So in the last lecture, we've been talking about a scenario where we have a classical optimization problem, and then we employed several agents to solve the problem, which requires finding values for a number of variables which collectively optimize certain performance metric. And we were looking at the assignment problem. The crucial aspect of the last lecture was we used a auction mechanism for the agents to collectively determine a solution which has the optimal value. In this lecture, we're going to look at another example where also auctions play an important role in solving a decentralized optimization problem. So suppose we have a server which is only available within a certain period in the day, and there are a number of jobs who want to use the server. However, the server can be used by at most one job at each hour. If the server is idle, then there's a certain amount of gain on the energy saved per hour. And also each job has a deadline, and you have to complete the job before the deadline in order to get the reward out of this job. So basically the formulation specifies a number of jobs. In each job there's a required length, so that specifies the integer value, which is the number of hours needed to complete this job. There's also a deadline, which is also an integer value indicating the hour before which the job has to be finished, and a net worth of the job, which is the amount of money that we will get if we finish the job in time. In this example, suppose that the server is available from 9 a.m. to 5 p.m. and also the energy per hour saved if the server is idle is $3. And we have 4 jobs with lengths 2 hours, 2 hours, 1 hour, and 4 hours each. And the table also indicates the deadlines and the worth of all of the jobs. So more formally, we can define a scheduling problem as a multi-agent system, and naturally each job will be considered as an agent. So we have, if we have n jobs, then we have n of such agents. We call them job agents. But moreover, we create this extra agent, and this agent is responsible for handling the idle period. So we call it the idle agent. So altogether, we have n plus 1 agents, ranged from 0 to n. And also each job agent is specified by deadline, or length, and a net worth, which are represented by D, lambda, and W, respectively. There's a domain, which is a set of time slots that the agents can purchase. And we assume that there are in total m discrete and consecutive time slots. The agents does not need to have consecutive periods of time, so that the job can be utilized. The job can be completed for a few hours, and then with some gap, and then a few hours afterward, and then a gap, and so on. So as long as before the deadline there is this number of hours allocated to the job, then this agent is happy. All right. So if you think about an illustration of this scenario, we had exactly the same as the previous example, the setup. We have these 4 agents, and this line indicates the deadline for each of the job, and also this number indicates the length of the job, and then we have the expected rewards from completing the job on time. And then we have these many time slots from 9 a.m. right to the end of 4 p.m. So that's just before 5 p.m. and each time slot has $3 reserve. That's sort of obtained. Well, that's the reward of the idle agent if this time slot is idle. So, what is the solution? The solution will be a schedule, which is a map that maps from time slots to agents. And it can be represented by this tuple of sets F0, F1 to Fn, where Fi consists of the set of time slots that are given to the ith agent, right? The total solution set is SCH. So we can, just like in the assignment problem, we can define the local reward function, which is a function that maps from the solution to the real numbers. And it's defined as follows. The reward for agent I, given that this agent receives the time slots in the set Fi. So if Fi includes lambda I hours before the dith time slot, or before and on the dith time slot, then this agent will get Wi, which is the net worth of the job. But if it doesn't, then this agent will get 0. Right? And this is for the job agents. For the idle agents, if given the set F0, which is the set of idle time slots, the reward for this agent will be the sum of the reserve price of all of these time slots. Right. In the previous example, the reserve price for every time slot is the same, which is $3. So this will be just the sum of the $3 for every idle time slot. So what is the evaluation? The global evaluation function is defined as a sum of the local reward for every agent. That includes also the idle agent, right? So that's the overall evaluation of a solution. And what do we want? We want to find a solution which maximizes the total reward, right? Just like in the assignment problem, we can alternatively formulate the problem using linear programming. In this case, we can create a variable xis. So this is created for every agent I for every subset S. So for every job I and for every subset S of time slots. The xis is defined to be 1 if the ith job is given the set of time slots S, and it's 0 otherwise. So again, this is just a binary variable, and it's representing whether S is given to I. Remember, S is a set of time slots, not a single time slot. It's a set of time slots. So the scheduling problem asks for an integral solution that satisfied this problem, where we have the objective function being the sum for all of the subset S of X for all of the agent I, the jobs I of VIS times XIS, subject to the sum of all of the XIS less or equal to 1. So for ranging from all of the S's. So this means that, of course, for any agent, it can be given to one set of time slots, right? And also, if you look at for every S, right, for every J in X, so for every time slot J, if you look at all of the agents who can receive time slot J and all of the S, all of the subsets of time slots that are given to agent I, if you sum that up, this is also bounded by 1. So this means that every time slot can be given to at most one agent. And also every XIS is bounded by 0 and 1. Right. So if we have this formulation that's equivalent to the problem that we want to solve, and an integer solution for this problem will correspond to a solution of the original problem, and of course one can use linear programming to solve this task. However, notice that the transformation from the original problem to this problem requires an exponential blowout, because we need to create a variable for every subset of X. So this problem is very, very large, and solving it can become impractical in actual applications. And in fact, we can prove that this problem is NP complete. So one would not hope to get a polynomial time algorithm. So we, just like in the assignment problem, recall that we defined this very crucial notion of competitive equilibria, which is the situation where all the agents are happy with the current allocation under the current price, right? So once again, we can introduce a similar notion. So now the setup is very similar to the previous case, where we imagine we have agents who enter this market, but instead of selling items, this market sells time slots to the jobs. And the difference between the previous cases, in the previous case, every agent can receive at most one item, but in this scenario, the agent can receive multiple time slots, right? So essentially, the bidding is made on bundles of time slots rather than single time slot. And we also can define this notion of competitive equilibrium as the state where under the current price of all the time slots, all the agents are obtaining their most favorable bundle of time slots. So formally, let P be a price vector. Recall that a price vector just give every time slot xj a price, pj. And of course, the time slots may have different price. And instead of allocating time slots to jobs, we imagine jobs as buyers of time slots. The utility of the ith job of getting time slot t will be equal to the local reward that job I receive from these time slots t, take away the sum of the price that is needed to pay for these time slots. So that's the utility, right? So that's almost the same as the assignment problem. For example, if we have these time slots and 4 jobs, then suppose on the right-hand side, you can see that we have defined a solution where the first 2 time slots are given to the second agent, and then the next 2 are given to the first agent, and then the remaining 4 are given to the last agent, and actually the third agent did not receive any time slots. Then, and also we have the current price of each of the time slots. You can see that the utility, for example, of the first agent will be equal to 0.5. Why? Well, first of all, he gets the 2 time slots that he desired. This is needed to complete the job before the deadline. But in order to get these time slots, he has to pay $9.5, and he gets $10 as reward, and therefore he has a net utility of 0.5. Right. If you look at the second agent, he also completed the task within the deadline, paying $12.5 for the 2 time slots, and he will get $16 as reward, and therefore the net utility will be 3.5. The third guy did not get any time, so he did not complete the task. But he also didn't spend anything, so he would just end up getting 0 utility, right? And the fourth guy will get 1.5 utility if you do the math. So what is a competitive equilibrium? Given a scheduling problem, a solution is in competitive equilibrium at certain price if the two conditions hold. The first condition sets a set of time slots to job I is utility maximizing. This means that you cannot get a higher utility if you receive a different bundle of time slots. Right, so the current time slots, Fi, will be the one that give this agent the maximum utility. So this is written as argmax. So this is the among all of the subset of X, look at the T, which gives this agent the highest utility, and that's our current Fi. And second condition is that the time slot is unallocated if and only if it has a reserve price. So this means that because we're starting at the reserve price, and we do not want to have a higher price than the reserve price if this time slot end up is not taken by anyone. Right? So F0 contains all of those time slots whose price will be equal to the reserve price. Right? If you look at this example, which I just described, that is in fact in competitive equilibrium. Of course, this is a bit hard to check. You have to look at all of the agents and all the alternative possible bundles. But soon you soon realize that everybody has received their best option. Notice that the third guy, even that the third guy did not get any time slot and did not finish the job, it doesn't mean that the third guy is not happy, right? Because in order to finish the job under the current price, there's no time slot that is under $6. Right? So if you want to complete the job and purchase any of these time slots before the deadline, he will need to pay at least 6.25, which gives him a utility of negative 0.25, which is worse than zero, right? So he has no incentive to really take further part in the market, right? So at this moment, even if he gets empty set of time slots, we can say that he's still happy, he still gets his optimal bundle, and if you look at the whole set of agents, they're actually in competitive equilibrium. And just like in the assignment problem, in the competitive equilibrium for scheduling problem, we still get this optimality. So if a solution F is in competitive equilibrium at this price, then F is necessarily optimal for the problem. So this is really, really good, because just like in the assignment problem, we have this direct connection between the locally optimal decisions of the individuals and the global optimal solution for the whole set of agents. And the proof is in fact not very difficult. It just uses the definition of the total reward function, and we go through a sequence of equality and inequalities to establish that for any other solution F prime, if F is in equilibrium, competitive equilibrium, then the total value that we get will be greater or equal to this any other solution, what we get from any other solution. So, but that seems to be a very good saying, but there are some bad news, which makes this problem very different from the assignment problem. Because as opposed to the assignment problem, for the scheduling problem, competitive equilibrium does not necessarily exist. You would be able to, for example, if you run, if you analyze the example that I give below, you will see that it's not possible for the agents to get in a state where they're in a competitive equilibrium. But there's actually some good news. competitive equilibrium exists for a special class of scheduling problem, namely what we call the single unit scheduling problem. This is when for every agent that the agent just need to get one time slot. So there exists a time slot such that for all of the bundles of time slots, the local reward for this agent getting this bundle would be the same as the agent getting just that single time slot, right? In other words, each agent desires only a single time slot. So in that case, this problem can be reduced to the assignment problem. And therefore, everything that's true for the assignment problem holds for this case. So a single unit scheduling problem has a competitive equilibrium. But this same does not hold in the general case, right? So we have this good news, but of course we want to still focus on the more general case. And is it possible, even though we cannot guarantee to reach competitive equilibrium because sometimes it doesn't exist, we still would like to find a schedule that is somehow good, right? And supposedly, can we find an algorithm that somehow reach competitive equilibrium if there is one? Right. We introduced this ascending auction algorithm, which is very different from the assignment problems auction mechanism. You can see that instead of inviting the agents to submit their bids, here the agent simply submitted an intention to make another bid, but the price that is the next price for the item would not be determined by the agent, but rather the price is determined by a fixed price increase mechanism, right? So the auctioneer has the power to advertise ask price. The agent bids the ask price for bundles of time slot. There is a fixed bid increment epsilon on the price, so we can guarantee that the price of each time slot will increase with every bid, and will stop when no agent has a profitable bid. Right. So, as an example, you can imagine here we have, all of these time slots. We have these 4 agents. And the auctioneer says that, well, now the price for every time slot would be $3. That would be the reserve price. And also, just prior to starting the auction, there is this epsilon, which is announced to all the agents saying every bid will increase the price of this time slot by $0.25. And then we can start. All right. So now let's think about it. Suppose we iterate the bidding process in the agent one by one. And first of all, the first agent will make a bid. And the first agent has the deadline, which is up to 12 o'clock. Right. So this agent will say, okay, I want to bid, and let's say just bid the first 2 time slots that are available. I want to bid 9, 10. Right. Notice that he only indicates which time slot he wants to bid, but he has no power to set the price because the price is fixed. If he bids 9 and 10, then necessarily in the next round, the price for these 2 time slots increase from $3 to $3.25. Right. So now the winner is the first agent getting these 2 time slots, and this will ensure that the agent will finish the job on time. And then we go on to the next round. The second agent also wants to finish the job, and also before the deadline, which is up to 11 a.m. And of course, since he's rational, he wants to bid the time slot with the lowest price so far. There's 11, which is $3, and then he has to choose one of these 2. It doesn't really matter. He can just choose, say, 10 a.m. So he bid on 10 a.m. and 11 a.m. And this will increase the price of 11 a.m. to 3.25 and increase the price of 10 a.m. to 3.5. So now these two time slots belong to the second job. The first job loses the second hour. And this means that the first job now has only 1 hour, which is not enough to finish the job. Right. And now let's go on to the third guy. The third guy says, well, because I have to finish everything before, and including 11 a.m. So I want to bid, and only the third job just need 1 hour. So he just bid on one with a smaller price, which could be just 9 a.m. So now he controls 9 a.m. and first guy is out, right? And then the last guy said, okay, he just bid on 12, 13, 14, 15 because they currently have the lowest price. And you notice that he has the latest deadline. So any of these time slots is good for this guy. So he gets all of these 4 time slots, right? So this finishes a round, and we continue to go back to the first guy. He bids on 11 and 12. If we repeat this process, so I'm not going to do that here, but we can see that eventually competitive equilibrium is reached, which end up the same solution as I illustrated to you earlier, and we just shown that this is in competitive equilibrium, right? So that seems to be a very good mechanism, which lead to competitive equilibrium for quite a general number of cases. So let's describe the algorithm using a pseudocode. We call this ascending auction algorithm. It has this initialization phase which sets the current bidding price as the reserve price for every time slot. And for every agent, initially we set the empty set as the bundle that's given to the agent. And then we enter this auction protocol. We repeat the iteration. So within the repeat, there's this one iteration. For every agent, I from 1 to n, this agent will make a bid. And for each time slot xj, if xj is already in the time slot given to the ith agent, then the price is fixed as bj. Otherwise, we increment the price to bj plus epsilon. So this is set by the auction mechanism. We need to increment the price. And then the agent, so this is actually quite a expensive operation, because you need to identify the bundle of time slots which gives the maximum utility, right? Remember the subtraction in this bracket expresses the utility of agent I. So this will be looking for the bundle S star, which gives the maximum utility to agent I. And then we look at each of the time slot that's in S star, but it's not currently held by agent I. And we need to make a bid on this time slot, right? So that's the operation, and eventually this bundle will be given to the ith agent, and that finishes one iteration of the auction, and this will repeat for every agent for this basically one round of bidding. And this is repeated until the solution does not change, right? And because the price of every item increments by a non-zero value, the auction, we can be guaranteed that it terminates within a finite number of rounds. So we will get a solution, but we want to analyze more property. So here we have this exercise. I would invite you to try running the ascending auction algorithm with epsilon equals to 1, and then see, first of all, would the process terminate? I've just told you that this process will terminate because the price will always increment. And would a competitive equilibrium be reached? Well, in fact, in this case, the answer is no. Right, so that's really a bad thing. If we set the epsilon to be small, in most cases we can reach competitive equilibrium. But if we set it too high, then there are some cases where we cannot reach competitive equilibrium. Also, there are some other bad news. For example, if you look at this very simple case, when we have two time slots, we have two agents, one demanding one time. Essentially, he demands only hour, which is the first hour available, and then the other agent need to have both hours. And suppose we run the auction mechanism with epsilon equals to 1, then you will get something quite bad. So first of all, what we get would not be the optimal schedule. And also, the solution that we get is in fact quite far away from the optimal schedule in terms of the total evaluation. So the total evaluation would be much smaller than what the optimal schedule would give us. Right? And in fact, theoretically, one can prove that there's no bound on the difference between the total reward that we get from this auction mechanism and the total reward that we get from the optimal schedule. There's no bound at all. So you cannot say anything good about the performance of this auction mechanism that I just introduced. So that's a bad scenario. I also invite you to work through this example yourself and see what I just claimed. So let me just summarize the facts that I listed above. The ascending auction algorithm cannot guarantee to reach competitive equilibrium for the scheduling problem, and may terminate with a result that's arbitrarily far from the optimal solution. That's all bad news, but like what I said, if we focus ourselves on single unit scheduling problem, then we get some good news. The ascending auction algorithm produces a solution to the single unit scheduling problem that is suboptimal by at most k times 1 plus k epsilon, where k is the minimum between m and n, right? So essentially this is using a reduction from this scheduling problem to assignment problem. All right, so that essentially finishes today's lecture. We've introduced this slightly more complex scenario of employing multi-agent system to solve a well-known optimization problem. This optimization problem is itself NP hot, and therefore all of the negative result is somehow not too surprising, right? Because the problem is inherently very difficult. So what you need to get from this lecture is, the definition of the problem. How do we employ the multi-agent system to solve the problem? The crucial thing is the definition of competitive equilibrium, which is very naturally extended from the assignment problem. And the crucial thing is that there's still this relation between locally optimal choices and the globally optimal solution. And but on the downside, in this case, we cannot guarantee that a competitive equilibrium always exists. And we designed this ascending auction algorithm, which failed for a number of cases. Right? Nevertheless, it's still an interesting mechanism and still is worthy to discuss. Right? So I'll see you in the next.